Hi, in this video we're going to compute the interfragmentary Vim between two wire structures. Vim is our new word for EMF. The term EMF is a misnomer because EMF is really a voltage. It's not really wise to call something that's a voltage a force. And this is not new to me. If you go to the previous video, you see that even the standards organizations have deprecated the term EMF, but we need something in its place, and so we came up with Vim. Vim is basically a word that means energy. Okay, this video is the sixth video of the New Electromagnetism V5 series, and New Electromagnetism V5 is the fourth paper of the EtherealMechanics series. So this video sequence number is EM0406. So in this video, we're going to define the interfragmentary Vim, then we're going to derive the interfragmentary Vim. Now, just so you know, in the previous older documents for New Electromagnetism version 4 and older, we still used the EMF, and we would call this fragment-to-fragment EMF or fragmentary EMF, and we still even may use the term fragment-to-fragment Vim going forward. But interfragmentary Vim is the new term because it says it with fewer letters and syllables, whatever. And then we'll show the experimental corroboration. Now, in this video, at the end, if you wait, I have a outline of where we're going, the forward, the future looking path of EtherealMechanics. And you may want to stick around for that to see how I think we're going to go forward. So the interfragmentary Vim is the voltage you would detect at a gap in a target loop due to the motion of a source loop that has a current in it. Okay, and what we always do for New Electromagnetism is we break these loops down into tiny little fragments and compute the effect of one fragment. And a fragment is a differential length. We just use the term fragment because it fits in the brain easier than differential length. It's easier to say. So we take a fragment of the source loop and we compute the effects on a fragment of the target loop. Later on, to get the full effect, we have to do a dual path integral over this entire system. But it's simple enough just to do the interfragmentary effects, get them down, and you do the integrations later. Okay, so from the third video in this series, we already computed the fragment to point magnetic force from a single fragment of the source loop carrying a current. And that model is this model here. And because of the cancellations that went on in the derivation, we find out we only really need to discuss or concern ourselves with the current in the source fragment. Okay, so what we're going to do now is we're going to take this fragment and we're going to apply it to the target fragment. But one thing that's interesting is our voltmeter that's attached to another portion of this loop is not going to register the unbalanced charges because they don't move. So what we're going to do is compute only the effect on the mobile carriers in the wire. So this is what we're going to consider. So the quantity of target conduction charges is found using this expression here. So we're going to substitute this expression into QT. And the velocity of the target charges is the combined velocity of the conduction current velocity, because this is relative to the wire, with the actual motion of the wire itself. So for the velocity of the target, we're going to put VTC plus VTW. And that's what it's going to look like. Now, we're going to convert it into an M field. I don't like the term, but that's what we've got, by dividing by the force by the target, the QTC. So basically this entire set of terms here, which you really don't need to substitute, we could just divide QTC out. That becomes this. Now this is interesting because when we compute the Vim, only the direction of this field in the direction of the length of the target is what matters. And so we're going to take this value and we're going to do a dot product of it by the differential length of the target. But something interesting happens. This term is very, very, very special. So we're going to take a little side we're going to take a little segue and explain what this term is. Okay, this term shows that if we have a source fragment and a target fragment, if you have a current in the target fragment going in this direction, and these things are stationary, let's say, so that these terms cancel out, well then if you follow the vortex expression here, if we take the angle from the radius to the direction of the source, from the radius to the direction of the source is a 90-degree rotation. Okay, and then we apply that to the direction of the target, which is 90 degrees, and so we rotate that 90 degrees. That turns out to be a force to the left. So what we have here is we have conduction that's orthogonal to the direction of current flow. And this is very interesting. Where else do we see this in physics? Well, that's called the Hall effect, because here is a Hall probe. If you induce current in a conductive patch, you apply a magnetic field to it, well, what you get is conduction orthogonal to the direction of the current flow. That's called the Hall effect, and that is how a Hall effect works. And what's interesting here is the Hall effect increases the faster the current moves through the patch. So if you make the patch very, very thin, basically increasing its resistance by making it thin, or by putting a resistive material here. I'm sure you've heard of magnetoresistive sensors, same idea. So the quicker the charges move, the more the effect is. And this, my friends, is the velocity of the charges in the conductor. If you work this out, that's what this is. So any way you can increase the velocity of the charges through this patch will increase the Hall effect felt orthogonal to the conduction. So that is what this term is. This term is the Hall effect. So for now, because we're going to be applying this to copper wires, which are good conductors, which minimizes the Hall effect, and because we're not discussing a target that has a significant current in it, there's very minimal, if any, Hall effect. And because the Hall effect is mostly, I mean, there are cases where it is in the direction, but they mostly cancel out. The effect is mostly orthogonal to the direction we are measuring the Vim, then for the most part we can ignore this effect for now. But we will come back to this term later when we will apply the new magnetism force model to the Hall effect experiment. And also there's going to be, when you have back EMFs or back VIMs in motors and generators. We may not get to that in this series, but there will be advanced applications of new electromagnetism later where we will cover that. So getting back to the interfragmentary Vim, we write the M field model here, and I don't like that term field, but okay. And we drop out the Hall effect term to leave just this, and then we dot product both sides by the differential length of the target, and we end up with our Vim. This is our fragmentary Vim. This is between two fragments of a target and a source. Now to apply this, we have to integrate that equation over the complete perimeter of a target and a source loop. And that gives us the total Vim that you would measure at the terminals of, that would give you the voltage you would measure at the terminals of a target loop, assuming there's no other reactances in the loop. Okay, now this has limitations because we're assuming these are good conductors. There's minimal target current. You are using uniform conductors. This is for filamentary source and target loops. We're doing this for low frequency, and the source and the target are not the same loop. Okay, so we always must put our limitations here because they don't really do this in physics, and I see physicists taking equations that have no business being used in things and they use them. And so we must always publish our limitations because we derived this under these conditions. If we want something else, well, we derive it under different conditions. Simple as that. Okay, so in the experimental compendium, I put the list of all the experiments we have now, or at least up to 7, and we have validation for this derivation are 2, 3, 4, and 5 here. And what it is we got two 10-centimeter long wires. The source carries 10,000 amps. The target carries nothing. They're separated by 3 centimeters, and the wire motion is 10 meters per second. So what it is, experiment 2, you move the source in. Experiment 3, you move the source out. Experiment number 4, you move the target in. Experiment number 5, you move the target out. And so we're covering all the possible motions between the sources and the targets. And you can see that we have pretty much 0 parts per million error. And this yellow here means we're comparing this against classical theory, which is derived by the Physics 1 software over here. When we actually have experimental data, this will not be yellow. Okay, and our reasoning right now is if we match classical theory, we consider that a win. But there are experiments that we will be getting into where classical theory does give the wrong answer. Or should I say that new electromagnetism V5 and classical theory give different answers. Okay, and then we will have an experiment to validate which one's closer to the experimental results. But when they match exactly like this, we're going to call that a win. Okay, so that's where we are with this one right now. So this set of experiments is very primitive. Really, we should have a lot more experiments to validate this model. And there are more experiments coming. What we need to do is we're going to be doing other experiments that update the magnetic model. So instead of using current carrying wires to validate this model, we're going to be using magnets to do that because they effectively have thousands of amps running through a magnet, which makes the experiments a lot easier to measure. Okay, but right now the objective for new electromagnetism V5 is just to know enough to complete the NEV5 paper and to validate the new Physics 2 software. Okay, we've already talked about the separate NEV5 compendium. That will be a living document that as we do every experiment, it'll be updated as we go. And we will be honest, if new electromagnetism V5 fails to match experimental results, it'll be declared as such. Okay, we are not like physicists where we have to get corroborating experiments in order to get our next round of funding. I don't want the lies. I want the truth. Okay, and we have to understand the 8th rule of acquisition. This is new for the 5th set, the 5th edition of the rules of acquisition, is the failure imperative. Failure is the fastest way forward. Embrace it. And my drill sergeant was always fond of saying when I was in the military, can't fix something if you don't know it's broke. Okay, we want to find the failures so that we can fix and update NEV5 so it matches experimental theory better. We're not going to sit there with blinders on if it fails. No way. I don't have time for bullshit. Okay, we want to get to the promised land where we can go diving in the ether and do fantastic things with it. We're not going to do it with lies. Okay, so that's who we are. So the next videos in the NEV5 paper, I'm thinking this is going to complete the NEV5 video series and the paper. We're going to do the new magnetism model. This is the V5 model. It's updated from the V3 model of magnets, where we're going to consider dynamic charge motion, Coriolis, centripetal, and Venturi charge motion. We're going to do the PDX wire experiments, which will corroborate all of this. We're going to do the Hall effects experiment, homopolar, and then that, I believe, should complete enough of NEV5 validation at that point. Now, if you remember our analogy for going forward, okay, we have to go up and down, and we fill in spots as we go up, learn more so we can fill in the spots as we go down. And that's how we're going to fill in all the holes in science. Okay, so our future series, we're going to be our upstroke. Okay, we're going to produce the 5th generation of the rules of acquisition, but this will be intermixed. It'll be sprinkled throughout all the other stuff. Okay, then we're going to do the cosmology. This will be our large-scale ether model release. And we're going to try to get the GAXM complete by the summer vacation or on the summer vacation of 2024. This will be the only experiment for the cosmology portion that we are going to run. Okay, the rest of cosmology theory will be bumped against observations already made and already known by astronomers. And we already have theoretical corroboration. We did this in the early video series released like 10 years ago. They're really crappy videos. I mean, we have crappy videos now, I admit that, but they were really crappy back then. Okay, so we already corroborate all of them, the stellar aberration, precession of Mercury, and we're going to validate that that we can validate that you don't need dark matter with the Gaxum experiment. And that should be enough to say, hey, we got the model that explains everything, from the little to the large. Okay, and then after that, we're going to focus solely on electromagnetic theory. I'm not going to be going back into cosmology because electromagnetic theory is where we're going to define our search for the ether. And then we're going to have one more set of research into magnetic and diamagnetic materials. I've already ordered a lot of stuff. We got it in hand in case there's a zombie apocalypse or somebody drops a bomb. That's not going to stop us. Okay, so that's going to be our upstroke, and then our downstroke is going to be ether hunting. Number one objective is to detect the motion relative to the medium. And if you've been paying attention to the derivations we've been doing, the answers are there. There's still some things we need to fill in, and that's part of our upstroke I just talked about. But the idea of how to do that is there. It is screaming at us. So anyway, for people that are not my Patreon members, don't sign up to be a Patreon member unless you have the stomach for a real quest. Like anything, we have our doldrums and we have our points where things are going well. Okay, this is like any quest, you get your ups and your downs. I want to thank my patrons for sticking with me through the thick and the thin. I hope you're happy with the progress we're making now. I've got not enough time to do all the crap I've got piled up. We got a lot of stuff piling up. Anyway, that's good. That's really good, and we got a lot to do. Anyway, thank you very much.